let's talk about LeChateliers Principle, which is where our lab is on tomorrow night, which is just absolutely wonderful and beautiful and easy because there's no math. LeChateliers Principle is a way to predict how a reaction that is at equilibrium will respond to you messing with it. Okay, so how will a reaction respond to you messing with it? Now, the key here is the reaction has to already be at equilibrium. You know, it has to have come to equilibrium, be in that dynamic state. And because equilibrium is dynamic, right? Remember, it's not static, it's dynamic. Reactants are still turning into products, but the products are turning back into reactants at the same rate, and you never notice it. So because reactions are dynamic, they can be messed with. Since they never stop, we can change something and cause the position of that equilibrium to have to move in response to that. And there are three ways that you can change the equilibrium of a system or mess with it. You can change the concentration of something. So you can add more reactant or take some of the reactant away. You can add more product or take some product away. We'll talk about what LeChat does with that. You can change the pressure or volume of a container. We'll talk about how LeChatelier responds to that. And you can change the temperature. We'll talk about how LeChatelier responds to that. So let's talk about the first one, concentration. Here's how I remember this. I remember add, away, and I remember take, towards. Those four words will get you so far with LeChat, like it's not even funny. Add, away, take, towards. Let me explain what that means. That means if this reaction, let's say this reaction right here is at equilibrium. If I add more N2O4, the equilibrium will shift away from it. So since N2O4 is a reactant, in order to consume that N2O4, the reaction will go away to the right and you will make more product. So adding more of a reactant shifts the equilibrium towards the product side. The reason for that is the LeChateliers principle is essentially saying that the reaction is going to try and undo what you just did. This reaction was at equilibrium, and now you jacked it up. And now if I add reactant, it's going to try and use it up and turn it into product so it can get back to equilibrium. Conversely, if I would add a product, if this reaction was at equilibrium, I added more NO2, it would shift away towards the reactant side, and I would make more N2O4. Okay. Now you can also remove something. You can take something. When you take something, if I take N2O4, then the reaction shifts towards what was taken, and this reaction would actually shift left. You would make reactants and lose products. If I had a way to get in there and selectively take away NO2, if I took NO2, then the reaction would shift to the right, okay, because it would try and regenerate what I took. Essentially, again, the reaction was at equilibrium. It was happy as a clam. I just took NO2 out of the system. It's going to try and regenerate that and reestablish the dynamic equilibrium it was at. In order to regenerate it, it's going to have to shift to the right. So it's going to go right to make more NO2. So add, away, take, towards. Add, away, take, towards. Let's do temperature. Add, away, take, towards works for temperature as well. But you have to know what it means to be exothermic and endothermic. An exothermic reaction, that's a reaction with a negative delta H. Remember that negative, if I told you that the reaction had a change in enthalpy of -50, that's exothermic. An exothermic reaction is a reaction that produces heat. It makes heat. So for an exothermic reaction, heat is a product. Okay, so I want you to actually do that. Like if a reaction is exothermic, I want you to write plus heat on the product side. Conversely, endothermic, then these would be values where delta H is positive. In an endothermic reaction where you have to add heat, heat has to enter the system in order for it to go. So in an endothermic reaction, if we add heat, Okay, heat would be a reactant. And if a reaction was endothermic, I would actually want you to write heat on the reactant side plus heat on the reactant side. And then what we can do is this. So this reaction, the Haber-Bosch reaction, is an exothermic reaction. We'll talk about that in some detail tomorrow before class. If you have an exothermic reaction and we heat it up, that is bad news bears. Okay, because generally, your desire as a chemist is to make as much product as possible. And if I add heat to an exothermic reaction, it'll shift me back to the left and my yield would actually go down. Okay, what you actually want to do if you have an exothermic reaction is you want to remove heat. If I take heat and heat's a product in an exothermic reaction, the equilibrium will shift towards what was taken and I will make more product. Okay, I will make more product that way. So if you're trying to increase the yield of an exothermic reaction, you actually want to cool the reaction down. Now you say, well, why don't we just cool down all exothermic reactions? Well, you got to remember, chemistry, it's like, there's two sides to every coin. You could unfortunately cool it down so much that it would slow it down. And now maybe the reaction doesn't happen, instead of taking 2 hours, now it takes 2 weeks and your boss isn't going to be happy about that. So it's a balancing act between the two. If we had a reaction, let's say A plus B goes to C, that was endothermic. Okay, so let's say this synthesis reaction was endothermic, has a value of positive 15 kilojoules or something for delta H. Their heat is a reactant. And if we heat up an endothermic reaction, that'll actually generate more product. Okay, this is what you would want to do. For an endothermic reaction, if you're looking to increase your yield, you actually want to heat it up. And that has the added benefit that when you heat it up, it actually goes faster then. So it should be done quicker. Now there are, you could heat it up so much that another undesired reaction now has enough energy to happen, and you could start to, make a secondary unwanted product, something like that. But in general, if you have an endothermic reaction, it's actually like, it happens faster and you increase your yield if you heat it up. Conversely, what you generally don't want to do is you don't want to cool down an endothermic reaction. If I put this endothermic reaction on ice, if I take heat and heat's a reactant, it shifts it back and my yield would go down. I would, have more reactants and less products, okay, to reestablish that dynamic state. So concentration and temperature, you can use add away, take towards, okay, and it's actually pretty sweet. When it comes to pressure, it's a little more complicated. So the pressure and volume of a system only depends upon the amount of gaseous reactants and products in the system. And again, LeChateliers Principle says the reaction that was at equilibrium is going to try and undo whatever you just did. So try and undo whatever you just did. So if I increase the pressure of a system, the system is going to try and bring the pressure back down. How would you bring a pressure down? Well, it would go to the side with fewer gaseous particles. That's what this statement right here is trying to say. If I would take a reaction that has gases in it, and I would increase the pressure, then it's going to shift to the side with less gaseous particles to try and reestablish an equilibrium. Conversely, and I'll talk about how we figure that out here in just a second. Conversely, if I decrease the pressure of a system, then the reaction is going to shift to the side with more gaseous equivalents to try and reestablish equilibrium. So if I decrease the pressure, the system's going to go to the side that has more gas particles to try and bring the pressure back up. Let me show you what that would look like. And then we'll talk about how volume works. We're going to have to use Boyle's law to talk about that. So here's how this would work. Let's look at this famous reaction that we'll talk about more tomorrow, the Haber-Bosch reaction. If I would take this system and I would increase the pressure. So imagine I have a piston here inside and I increase the pressure. Okay, and now I'm going to force these guys to occupy a smaller space. If I increase the pressure, LeChateliers Principle says the system is going to try and bring the pressure back down. Now, how could it possibly bring the pressure back down? Well, the reactant side of this equation has 4 gaseous equivalents. See that 1 plus 3 is 4. whereas the product side only has 2 gaseous equivalents. So what it could do to try and bring the pressure back down is it could shift to, in this case, the right, because the right side has less, 2 gaseous equivalents, than the left side, 4 gaseous equivalents. How is that going to bring the pressure down? Well, think about it. For every 4 reactant molecules we would take away, all right, for every time we do a reaction, so an N2 goes away, and 3 of these H2s go away. So that's 4 things went away. Those red things are now gone. You only get back 2 things. So we're going to add 2 greens. So think about that. Taking away 4, adding 2, you're going to have less particles in there. You essentially just cut the number of particles. Every time you do that, you lost half of your particles. Less particles flying around there, less collisions with the walls of the container. That's what pressure is. That's how shifting to the side with less gaseous equivalents brings your pressure back down. Conversely, if we would decrease the pressure, so if we would, if we'd increase the volume and decrease the pressure, these guys now have more space to fly around. If I decrease the pressure, the system's going to try and bring the pressure back up. It's going to try and undo what you just did. And the way it can bring the pressure back up is to shift to the side with more gaseous equivalents. The left has 4, the right has 2. So it would shift to the left side in this case. So I would lose NH3 and I would gain N2 and H2. So I would go to the left. Now, how does volume work in this? Well, you have to remember Boyle's law from Chem 101. Boyle's law says that pressure and volume are inversely proportional. So here's how I treat these problems. If I tell you that the volume decreases, then I just say, the heck with that. That means pressure increases. I always think about it in terms of pressure. If I tell you that the volume of the system increases, the heck with that. That means the pressure decreases. Robert Boyle said pressure and volume are inversely proportional. So if I tell you something about the volume, you should be able to turn that into a pressure. So one more time here, real quick, for this system, we'll answer these 4 questions here, and then we'll get you out of here. And then we'll practice it some tomorrow, too, after we do the extra small assumption. If in this system, we have 4 gaseous equivalents on the left, and we have 2 gaseous equivalents on the right. If the pressure increases, LeChat says, we're going to try and bring that pressure back down. That's going to shift to the right because there's less gas over there. If the pressure decreases, LeChat says, we're going to try and bring that pressure back up. That's going to shift to the left because there's more gas. So there's more gaseous equivalents over there. For 3 and 4 here, if the volume increases, I don't play that game. If volume increases, that means pressure decreases. And if pressure decreases, that's the same as scenario 2. We're going left. And if volume decreases, that means pressure increases. We're going to try and bring the pressure back down. That's the same as scenario 1. We're going right. So that's how I tackle those problems.